Section. Introduction. Let's dive into the fascinating world of generative AI. The recent advancements in this field, from ChatGPT to GPT-4 to DALL-E 2/3 to Midjourney, have caught the world's attention. People are both thrilled about the potential applications and worried about the risks of AI that seems to surpass human intelligence. These AI models can generate outputs in language and visual domains in seconds, outputs that could challenge experts with years of experience. This has led some to claim that these models have outperformed human intelligence. However, these models also make basic mistakes that even non-experts wouldn't make. This leads us to a paradox. How can these models have such advanced capabilities yet still make fundamental errors? We believe this paradox arises because the abilities of today's generative models differ from human intelligence. We propose the generative AI paradox hypothesis. These models, trained to reproduce expert-like outputs, can generate outputs that are not dependent on their understanding of those outputs. This is different from humans, where understanding is usually a prerequisite for generating expert-level outputs. We tested this hypothesis by conducting experiments to analyze the generation and understanding capabilities of these models in both language and visual domains. We looked at understanding from two perspectives. 1. Can the models choose the correct responses in a task similar to the one they were trained on? And 2. Can the models answer questions about the content and appropriateness of their generated response? Our results showed that while models often match or even outperform humans in generating tasks, they fall short in understanding tasks. We also found that understanding is more closely linked to generation in humans than in AI models. Furthermore, human understanding is more resilient to adversarial inputs, with the gap between model and human understanding increasing as the task becomes more difficult. We also noticed that although models can generate high-quality outputs, they often make mistakes when asked questions about those outputs. This suggests that their understanding is not as good as their generation. We believe this difference in capabilities between generative models and humans could be due to the training objectives of the models and the size and nature of the input. Our findings have broader implications. They suggest that our current understanding of intelligence, based on human experience, may not apply to artificial intelligence. While AI capabilities often seem to mimic or surpass human intelligence, the actual landscape of capabilities may be fundamentally different from human cognition. We also caution against using generative models to gain insights into human intelligence and cognition, as the mechanisms behind the seemingly expert human-like outputs may not be human-like. In summary, the generative AI paradox suggests that we should study models as a fascinating contrast to human intelligence, rather than as a parallel. To test the generative AI paradox, we need to define what we mean by generation and understanding. Generation is the production of content in response to a given task input. Performance in generation can be evaluated automatically or by humans. Understanding, on the other hand, is not defined by an observable output, but can be tested by defining its effects. We measure understanding by asking two questions. 1. Can models select accurate answers from a set of candidates in a task similar to the one they were trained on? And 2. Can models accurately respond to questions about the content and appropriateness of their generated output? These definitions provide us with a framework for evaluating the generative AI paradox, allowing us to test whether the hypothesis holds across different tasks and models. Section Summary. The recent advancements in generative AI have led to models that can produce outputs challenging even the expertise of humans, raising concerns about their superhuman capabilities. However, these models often exhibit errors in understanding that even non-expert humans would not make. This paradox arises because generative models can acquire the ability to generate expert-level outputs without fully understanding them, unlike humans who require understanding as a prerequisite for generating such outputs. Section. Experimental Overview. In this section, we'll provide a simplified overview of our experimental approach, which is guided by the definitions we've previously discussed. We'll be testing two sub-hypotheses across various experimental settings and will provide details that apply across all experiments. Our first task is to evaluate a hypothesis for a specific task. To do this, we need to establish a human baseline, which is the level of understanding we expect from a human who has the same ability to generate responses as the model. We'll explain how we establish this baseline for both types of understanding we've discussed, resulting in two sub-hypotheses. In our first evaluation method, we directly measure human performance in generating responses and understanding them to establish a baseline. We consider the hypothesis to be true if the models perform worse in understanding compared to humans who have the same or lower response generation performance. In simpler terms, our first sub-hypothesis is that models can generate responses as well as or better than humans, but they fall behind when it comes to understanding. In our second evaluation method, we assume that humans can answer simple questions about their own responses. We then test how accurate models are at answering questions about responses they've generated. We assume that humans would be nearly perfect at answering such questions about their own responses. So, our second sub-hypothesis is that models have difficulty answering simple questions about the content they've generated, which humans could answer for their own responses. In our study, we focus on the most advanced generative models, which are the ones that are currently attracting the most interest and concern. We examine both language and vision models, as these are areas where significant progress has been made recently. For language, we use GPT-4 and GPT-3.5 for both generating responses and understanding them. In the vision domain, the best models for generating and understanding are usually different. We use Midjourney for generation, and Clip, OpenClip, BLIP2, Bing Chat, and Bard for understanding. We conduct experiments for both sub-hypotheses, examining tasks with selective evaluation of understanding, sub-hypothesis 1, and tasks with interrogative evaluation of understanding, sub-hypothesis 2. Both sections include tasks related to language and vision. Next, we compare the performance of models and humans in generating responses and understanding them. We use a variety of benchmarks for our tasks, including open-ended dialogue datasets, reading comprehension tasks, summarization tasks, common sense benchmarks, and natural language inference tasks for language. For image generation, we use text prompts from 4 benchmarks. For each task and modality, we consider 2 settings: generative, where we ask models to generate a response based on task-specific inputs, and discriminative, where we ask models to select the correct answer from a set of options. We use human evaluations to judge the correctness of responses in the generative setting and report the percentage of successful responses. In the discriminative setting, we report the accuracy of choosing the correct response from the options. Our results show that for 10 out of 13 datasets, at least one model supports sub-hypothesis 1, with models outperforming humans in generation but underperforming in understanding. For 7 out of 13 datasets, both models support this sub-hypothesis. In the vision domain, we find that AI models exceed average humans at generation but lag at understanding. Section summary. In this section, the authors provide an overview of their experimental approach. They propose 2 sub-hypotheses to test across different experimental settings, one focusing on models' generation and discrimination capabilities in language tasks, and the other on models' ability to answer questions about generated content in vision tasks. They conduct experiments using state-of-the-art generative models such as GPT-4 and GPT-3.5 for language tasks, and Midjourney, Clip, and OpenClip for vision tasks. The results support the sub-hypotheses, showing that models excel at generation but underperform in discrimination and understanding compared to humans. Section. Models fall further short of human performance with harder discrimination tasks. We've noticed that artificial intelligence models tend to struggle more than humans when it comes to more challenging discrimination tasks. To understand this better, we've looked at 2 types of negative examples: hard negatives, which are subtly incorrect and require a deep understanding of the task to identify, and easy negatives, which are clearly wrong because they're far removed from the question's topic. When we compared the performance of the GPT-4 model and humans, we found that as the complexity of the candidate answers increased, the model's performance gradually decreased. For example, in the XSUM task, GPT-4 was 100% accurate when choosing the correct answer from easy negatives, but this dropped to 19% when faced with hard negatives. We noticed that the models made the most mistakes when the responses were long and complex, such as summarizing lengthy documents. Humans, on the other hand, were able to maintain a high level of accuracy regardless of the difficulty level. We also compared the performance of the OpenClip model and humans across different difficulty levels. Just like with the language results, we found that while humans performed consistently well across both hard and easy negative settings, the model's performance dropped significantly when faced with hard negatives, from 100% to around 69%. This suggests that humans are better at identifying the correct answers even when the examples are challenging or adversarial, and raises questions about how well these models truly understand the task. Interestingly, when we asked workers to compare machine-generated and human-generated answers in language-related tasks, they often preferred the responses from GPT-4 over those generated by humans. The reasons they gave included longer response length, more elegant writing style, and being more informative, while human responses were preferred for their brevity and conciseness. This highlights the difference in capabilities between models and humans, with models excelling at generation and humans at understanding-based tasks. In the next part of our study, we wanted to see how well models could understand the content they generated. We prompted models to generate a paragraph using task-specific background information, and then asked them multiple-choice questions about the information they had generated. We found that while the models were good at generating content, they often made mistakes when answering questions about their own content, suggesting a lack of understanding. Humans, on the other hand, were consistently more accurate in answering questions about the model's content. We also conducted a similar evaluation on image understanding models. We asked the Midjourney model to generate images based on text prompts, and then asked other models to answer questions about the generated images. We found that while the image generation models were able to produce high-quality images quickly, they struggled to answer simple questions about the elements in the images. This suggests a gap between the ability to generate content and the ability to understand it in Vision AI, similar to what we observed in the language models. In conclusion, our results highlight the differences in capabilities between humans and AI models. While models excel at generating content, they struggle with understanding-based tasks, especially when the tasks become more complex. This raises questions about the true extent of these models' understanding and suggests areas for future research. Section Summary. Models often struggle to match human performance in discrimination tasks, particularly when faced with challenging examples, hard negatives, that require a deep understanding of the task. Humans consistently outperform models in maintaining accuracy across different levels of difficulty, highlighting the model's limited understanding. Additionally, while models excel at generating accurate answers, they often fail to demonstrate meaningful understanding of their own generations when asked questions about the generated content. This performance gap between models and humans is also observed in the visual modality, where image understanding models fall short of human accuracy in answering questions about generated images. Section. Discussion. Let's talk about the intriguing paradox we found in generative AI. Our experiments show that while AI models can often generate text and images better than humans, they struggle when it comes to tasks that require discrimination or answering questions about the content they've generated. Interestingly, we found that humans are better at linking generation and discrimination tasks, and they're also more resilient when faced with challenging inputs. These patterns vary depending on the task and the medium, but overall, our findings strongly suggest that AI models can generate content more effectively than they can understand it, especially when compared to humans. So, what could be causing this paradox? Why are AI models so good at generating content but not as good at understanding it? We have a few theories. One is that generative AI is designed to recreate the training distribution, not necessarily to understand it. Human learning, on the other hand, goes beyond simple replication. Another point to consider is that while we often treat AI models as individuals, they're actually designed to mimic a medium, like text from multiple authors. This means they're more likely to prioritize overall style and document wide features over the details that are crucial for understanding tasks. Also, the sheer volume and diversity of data that AI models are trained on could be a factor. For example, it would take a human over 32 years just to read all of Wikipedia, but an AI model can be trained on this amount of data and more. This could lead AI models to rely on existing solutions to problems, while humans have to use understanding and reasoning to answer the same questions correctly. We also need to consider the influence of evolutionary and economic pressures on AI development. For example, popular language models tend to favor English because it's the most widely used language in NLP, and therefore offers the most rewards for improvement. Similar pressures could lead to decisions that prioritize generation over understanding, as generation is more challenging for humans and thus more valuable. Of course, our study has its limitations. For one, we only looked at a small selection of the most popular models. Future research should explore a wider range of models, including smaller or weaker ones. We also focused on comparing model performance to human performance, but future studies could delve deeper into this comparison. We recommend that comparing AI models to humans becomes a standard practice, to help us understand when models can and can't replicate human capabilities. Finally, we only looked at one difference between humans and AI models. There are likely many other points of divergence, and exploring these will be crucial for addressing concerns and managing expectations about AI. Previous research has also explored the paradoxes and inconsistencies in large language models. For example, some studies have found that models can identify mistakes in their own generations, and others have shown that models can generate correct facts but also their negations. There's also evidence to suggest that models struggle with basic tasks like multiplication and often make inconsistent predictions. In terms of how AI models compare to human cognitive mechanisms, the jury is still out. Some studies have found that while infants can reason about the causes of actions by an agent, models can't replicate this. Others have shown discrepancies between human and model capacities in physical common sense reasoning. All of this points to the need for more research into the differences between artificial and natural intelligence.